All right. Did you still remember the Markovian equivalent model that I showed you in the previous example? I show you straight off the simple diagram where the conditional independence pattern of the black node here are just the same for this three situation if you control the red node in the middle here. And we summarize three of this situation into a new model where we call it the Markovian equivalent model. And this is quite the same for the picture here, but here none of the dependence can be further determined as coded direction. But the good news is since we're still in a system without unmeasured common cause, so we can still say the Riemann correlation is equal to causation, but we are not so lucky as we're in the linear confounders one. So this is the point about the mentioned diversity and complexity. And let me show you a quick look in the following. And I know this is a bit overwhelming because you see there are a bunch of causal diagrams here, even if we only add one Lennon confounder. So it's a bit confusing if we still use the Markovian equivalent to talk about so many situations. So instead, let's try to incorporate the concepts of inducing pace into the Markovian equivalents. And we got the inducing pace equivalent. And you see the circle, the small circle I added into the end of the line or the end of the arrows here means we can possibly describe different situation. For example, we can have the arrow goes like this one. Sorry, goes like this one or this one, but at least not this one. Remember, I talked about different layers of the meaning of the inducing pace in the previous episode, right? So, given that sense, we are sort of, we can at least exclude some of the situations from this big picture. So this will help us to better describe a more complicated situation and narrow down the range about the diagrams we are searching. Okay, so finally, I want to talk a bit about the causal discovery algorithm. You see here, by setting different objects when the system is without linear confounders, we are looking for a Markovian equivalent. And when there is some unmeasured common cause, we're seeking for the inducing pace equivalence. And, and similarly, when it comes to the algorithms, we have the SGS algorithms and the CI algorithm. And based on these algorithms, we develop more advanced algorithms such as the PC algorithms and the FCA algorithms. You probably heard of this if you are quite familiar about causal discovery. And from the SGS algorithm to the PC algorithms, it is because, for example, no matter we are looking for the Markovian equivalence or the inducing pace equivalence, the same thing we're going to do is to find out the patterns of conditional independent tests. The patterns of conditional independence, right? So, um, so from SGS algorithm to PC algorithms, the point is we teach the machine to quickly find out these patterns of conditional independence. Okay. You see here, I didn't talk about much details about these algorithms because there has been so many awesome materials talking about the causal discovery algorithms. But my point is, we can see here, depending on different types of causal diagrams we are looking for, we can see how these algorithms were developed and move forward into this more advanced version. Okay, that's it. In the next part, let's talk about the another advanced concepts, which was called is the tie-trie constraint.